In the last lecture, we were talking about chemical kinetics problem, and two distinct cases I have dealt, so that in a generic way, so that you can solve problems when diffusion through the solid will be given as a rate limiting step during for reduction or oxidation of a solid in a gaseous environment, or the boundary layer mass transfer being the rate limiting step. So, the treatment is going to be identical depending on the nature of the problem. So, in the context of solid liquid mass transfer, if the phenomena is boundary layer mass transfer control, whatever I have discussed in the last lecture would be applicable in a straightforward way. And while I left you yesterday and I told that I want to discuss a case to show you that how we tackle problems with having mixed control, and I said that I would like to discuss a case where boundary layer mass transfer and chemical reaction both determine the rate of nickel oxide reduction. So, let us pose the problem, the same problem that we were talking about. So, this is our changing. You must be knowing that what I am drawing is a topochemical model. Okay, this the front, the reaction front is parallel or analogous to having a shape analogous to that of the original sphere. Okay, so we have the boundary layer. So, that is there, and I said that there is a chemical reaction, and I have written that chemical reaction nickel oxide solid plus hydrogen, and the same problem that I am posing as yesterday, nickel solid and H2O, and the condition is that Pt is 1 atmosphere, okay, the total pressure, and temperature is 700 degree centigrade or 973 Kelvin. Okay, that is. And I have also explained the setup to you, that it is really the particle of sphere is hanging in a thermogravimetric setup, gas is flowing, okay, and as the gas flows, a boundary layer is created. Through the boundary layer, hydrogen diffuses, and case 1 was that the diffusion of hydrogen or transport of hydrogen more specifically through the boundary layer being the rate limiting, we have dealt that. Second case was that the transport was not important through the boundary layer, transport through the boundary layer was not important, rather we considered diffusion through this reduced nickel layer to be rate limiting, and that treatment was given, and the residual core is. So, we have a bulk concentration which I set as pH2O divided by pH2 bulk, and that was given in the problem, and we will continue to apply this particular condition. Only thing we are changing here is that instead of one, we will have two different rate limiting kinetic steps. So, since there is it is a boundary layer controlled as well as mass transfer control, so we would assume that this 9 value is going to be prevalent right up to the interface, and from here to here there is going to be a drop because the boundary layer is controlling the rate. So, it has finite resistance. So, therefore, there is going to be some kind of a drop here, okay, and the concentration is here is exactly same as it is here. Then we encounter the surface, and I do not know the concentration at the surface, okay. And then we have a diffusion process, but that diffusion for the given problem is not to be considered because we are considering that boundary layer mass transfer and chemical reaction jointly, interfacial chemical reaction, more specifically chemical reaction jointly determine the problem, rate of reduction. So, therefore, we understand, because I mean, you cannot solve a problem too mechanically, then you do not understand, then you do not see the beauty of the analytical treatment. So, because diffusion is not there under the given condition, so therefore, we can assume a diffusion. What drives diffusion? The concentration gradient. So, if diffusion is not there, that means this concentration must be identical to the interfacial concentration, and therefore, we can say that this is pH2O, okay, and we can say this is the surface concentration, and this surface concentration is same as this. But as I have indicated, this surface concentration is now not dictated by the thermodynamic equilibrium of this reaction, because the reaction has a finite rate. Reaction is not operating close to equilibrium, and therefore, it is determined, it is controlling the rate. It is one of the rate limiting kinetic steps. So, therefore, we can say that this concentration remains now unknown, and that poses an additional problem, because we have to calculate the rate and we have to calculate this concentration, because that drives the mass transfer across the boundary layer, as well as, which is analogous to this concentration, that determines the rate of the chemical reaction. Now, if you look at the expression for the flux small, okay, of hydrogen, then that flux is going to be mass transfer coefficient determined by pH2O, which is bulk, minus pH2O as per my discussion, that is the surface concentration, okay, and it is this concentration that I am referring to as the surface concentration, and this, for the mathematical treatment of the subject, is actually, as I have written, and now with more clarity, it is this, the surface concentration. That is what it is, and that is not known, that is neither dictated by thermodynamic equilibrium, okay. And also we can say that the rate of chemical reaction is rate constant, and if we assume, for the sake of simplicity, it does not mean that if we assume otherwise we cannot solve the problem, but for mathematical simplicity, let us assume that the chemical reaction is of first order. That information will be provided to you all the time, because order of a reaction is a experimentally determined parameter. So, we would say, therefore, it is the surface concentration, okay. That is what the reaction, a chemical reaction actually is seeing, the concentration which is not the bulk concentration, which is the surface concentration, okay. So, and this rate, okay, as you can see here, because there is no area here, this is actually a flux expression, and similarly this rate is also kg moles per second, kg moles per meter square per second. So, that is the rate, and this, because these two rates are identical, and why they are identical? Because whatever gases are diffusing, okay, that gases is getting consumed reacting here, because those gases cannot be accumulated onto the surface, because this surface have finite area. So, limited amount of gas is accumulated on the surface, and on the basis of that hypothesis we can say n is approximately, it is a reasonable assumption, the rate of the reaction, okay. And that allows us that if we now manipulate the two, we can find out that the rate of the reaction can be given in terms of the mass transfer coefficient, okay, and divided by Km and Km plus Kr into concentration of H2O at the bulk, and because I have used partial pressure, so I would write RT. So, there also, I think I have written somewhere, okay, here. So, this term should be divided by RT. So, that we have moles per unit volume unit, okay. So, moles per unit volume, okay, this is mass transfer coefficient, mass meters per second. So, meter and meter cube. So, the final unit will come out to be kg moles per meter square per second. That is what is going to come out from here, and this is RT has appeared because I wanted to convert concentration from one unit to other by using the ideal gas approximations. So, now I pose the problem that let us suppose that it is given that the two rate constants are more or less identical. Under the condition, estimate the rate of the process with all the data that I have given. Now, if the two rates are identical, okay, in that case you can say that this is becoming equal to Km, half of Km into pH2 bulk by RT, okay. And this R, as I have indicated, has a unit of kg mole per meter square. So, that is basically the flux. Now, in the previous problem we have calculated the mass transfer coefficient, and the value of mass transfer coefficient, if you remember, are referred to the last lecture notes. Okay, last lecture, you can see that this is given to be something like 0.174 meter per second. That is what under the given meters per second. For the gas flow rate through the tube furnace, okay, we could have a corrected gas flow rate, and based on the basis of the diameter of the tube furnace, I have calculated the mass transfer coefficient, okay, via the Range-Marshall correlation that have been described in the last lecture itself. So, therefore, plugging in this value, and because pH2O in the bulk, this should be pH2, because I was calculating hydrogen. Diffusion of hydrogen is the rate limiting step. Okay. So, one can do it with respect to pH2 also, because there is a molarity, 1 mole of hydrogen consuming. Numerically, the answer is not going to be different whether you treat H2O or H2 in the mathematical expressions, but under the conditions that we said that diffusion of hydrogen through the boundary layer is the rate limiting, it is perhaps desirable to write it not in terms of H2O, but in terms of H2, although the answer will come out to be identical. Okay. So, this pH2 bulk, that what we have seen yesterday, is exactly equal to 0.1 atmosphere, okay, and R is equal to 82.06 meter cube atmosphere divided by kg mole per Kelvin, that is the unit of R, and then you put the value of temperature which is 973, and then you can get the value with Km set equal to 0.174. So, the final value comes out to be half multiplied by 0.174 multiplied by 0.1 for pH2O divided by 82.06 into 10 to the power minus 3 multiplied by 973. And as I have indicated, the unit is already given here, and if you look at the value, this value comes out to be 1.08 multiplied by 10 raised to the power minus 4 kg mole per meter square per second. That is the rate of reaction. Now, I want to draw your attention to one important aspect. In the yesterday's lecture, when I was talking about only mass transfer as the rate limiting step, I calculated the rate of reduction, and the rate of reduction was calculated to be 6.18 into 10 raised to the power minus 8 kg moles per second, kg mole of hydrogen, or which is equal to kg mole of nickel oxide. Okay. Now, we divide it by 4 pi r square, and then what we get is 6.18 into 10 to the power minus 8 into 4 pi, and radius of the sphere is 0.005 squared, okay, and then the unit becomes kg mole per meter square per second. And if you do this operation, we find out that this value comes out to be approximately 2 times 2 into 10 to the power minus 4 kg mole per meter square per second, kg, because I have divided by the area. So, this is 4 pi r square. So, this is the dimension of meter square, and that meter square appears here. And now, you see the interesting thing that the rate has come out to be exactly half here of the value, because we have assumed that the two rate constants are identical. So, because they are operating in series, okay, earlier it was 1 and now it is 1 plus 1 2. So, obviously, there is going to be a 1:1 correspondence between the two cases. So, therefore, based on such things, many times we formulate objective type questions. For example, we say that given that the rate of in a mixed control process, if the rate of mixed control process where chemical reaction and mass transfer governs the rate of reduction, okay, the mixed control rate is going to be 2 times 4 times identical to, for example, the rate of mass transfer processes. So, from these exercises, if you can extract those kind of informations, otherwise you will have to do all these exercises in order to find out whether it is 2 times, 1 time identical or 4 times, and this calculation shows, and if you can get that message. So, I would suggest that every time, particularly those students who are very keen to learn the subjects, I think every problem carries certain messages, and I would like you to solve the problems and then note down that what you have learned from that problem, and that will reinforce your understanding of the subject as well as increase your analytical skill to tackle more complex problems in the same area, and so on and so forth. So, I think what we can see here, that the expression that I have written, if you remember, you can see that this expression can be written is just like, because they are in series. So, the analogy, electrical analogy kind of a resistance really comes into the picture. So, only thing we have to see that these are the sum of the resistances H2O bulk by RT. Okay. So, if you have now, if you include diffusion, you should be able to have a corresponding resistance to diffusion, okay, or the resistance offered by this particular region embedded into the equation. So, you just keep on summing up the individual resistances, and that is what this is the resistance to 1 by Kr is the resistance to chemical reaction, 1 by Km is the resistance to mass transfer, and similarly if you just add up. So, and the same thing, just like the way we have equated the two things to determine this surface concentration, similarly in the case of diffusion you will require this concentration, which is same, this concentration and this concentration, and in the case of when you will include the third step also as a rate limiting step, then this concentration and this concentration are no more going to be identical. So, you require a third equation, and that third equation is the diffusion flux equation, okay? And then by manipulating this you would be able to eliminate these unknown concentrations, and everything can be expressed in terms of the bulk concentration which is actually given to us, and the final derivation you can logically understand would be an extension of this particular equation, where we will just add up the corresponding resistance in appropriate units. We must realize that we have to check that the units of these rate constants are same, then only we should be able to add. That is a different subject, we do not deal, and in the whole exercise we have assumed that the rate constants, the order of the reaction is given to us, and we have dealt it with first order, and that is what most of the time we do for metallurgical process calculations, unless it is explicitly stated. So, with this I think I would like to wind up my discussion on reaction kinetics or problems dealing with reaction kinetics. And now, as far as process metallurgical problems are concerned, certain certain elementary expertise on fluid dynamic theories are also important, okay, and many a times we encounter small easy questions or elementary level questions on fluid flow, macroscopic mass, momentum and energy balance, and I would like to discuss for the next 1.5 lecture or so certain key elements which you are supposed to know and remember as far as your knowledge of fluid dynamics is concerned. Fluid statics generally, whatever you have learned in grade 12 stage suffices. So, I am not interested to talk on that because we have limited time. So, we will talk about fluid flow, basically what you are supposed to know, given that we do not, metallurgists do not per se does a full-fledged undergraduate course on fluid mechanics, but nonetheless in a course like transport phenomena, which is frequently taught in metallurgical curriculum these days, topics like fully developed flow is treated well, and also topics like macroscopic mass, momentum and energy balance. So, on these two headings I would like to momentum and energy balance, mechanical energy balance rather, this is okay, let me write mechanical energy balance. Heat transfer we have done, mass transfer we have done, chemical kinetics we have done, material balance we have done, and now I think with these two topics discussed, you will have a reasonably good overview of the kind of problems that you would encounter in process metallurgy. Fully developed flows, most of you have read. I think even though we have gone through only 7, 8 or 9 lectures in a rate process course, fully developed flow analysis is done, and particularly the textbook problem perhaps all of you have been exposed to is the Hagen-Poiseuille equation, flow through a horizontal pipe of having circular cross section. Okay. So, the parabolic velocity, classical parabolic velocity profile that you have seen. So, those kind of treatments are already explained to you, and I think you are expected to remember certain aspects of the fully developed flows. Okay. It is that the governing equations, the Navier Stokes equations, you should be able to offhand simplify, or you should be able to write, and before doing so you must understand that what is fully developed flow. Okay. And we are always dealing with one dimensional fully developed flow, constant properties, steady state, and these are unstated, though unstated, always apply. And fully developed flow, particularly many problems we solve. Okay. Flow between parallel plates driven by pressure gradient, flow through a circular pipe driven by pressure gradient, flow between parallel plates driven by with only one plate moving, flow between parallel plates when both the plates are moving in opposite direction. All these classical problems, flow between two concentric cylinders, which resembles very closely with our setup of a rotating viscometer, for example. All these kinds of depending on where you have been taught in the fluid dynamics course, all this analysis. And the velocity profile, basically 3 things we calculate. We calculate the velocity distribution. Okay. Second is we calculate the average flow, how much of liquid is flowing out, and we also calculate wall shear stress. These are the 3 kinds of general calculations that we basically do in the context of fully developed flow as far as metallurgical engineers are concerned. So, let us see that a fully developed flow between a parallel plate, infinite parallel plate, and I am just saying that what is expected you to know about the generic in a generic way about the fully developed flow. So, I would say that every time when you draw so this is the center line. Okay. So, these are parallel plates, flow between parallel plates. I would suggest that the first thing to do is to draw a coordinate system. Okay, that what you want to do is a parallel plate. So, you will do a Cartesian coordinate system. So, let us say that you can set anywhere, the origin may be set here, the origin may be set here, okay, depending on your convenience. So, you can say there are 2 directions, one is which is called the flow is coming in this way. Okay. So, this is called the streamwise direction. So, we say that this is let us say this is x and then this is y. Let us put that the origin is here. Okay. That is what it is. And let us say that this plate is being moving with respect to with a constant velocity along the streamwise direction, and as a result of which the flow is induced, and suppose we want to calculate the wall shear stress. It is given that at y is equal to 0 and this is y is equal to say 10 centimeter. Suppose water is flowing through this and water has a viscosity which is in CGS unit gram per centimeter second. that is what it is. The velocity that I have average velocity. So, we have or I can say this is u is equal to 10 centimeter. The velocity with which the top plate is pulled, okay. This bottom plate is stationary, top plate is pulled, and we want to do a fully developed flow analysis. The flow is assumed to be having constant property, it is a one dimensional flow, there is only Vx component of flow, there is no Vy component of flow, Vy is 0, and there is a gradient of the Vx velocity along the y direction. And suppose it is a given this data, compute the shear stress at, which is defined as tau yx at y is equal to 0, and this is dvx dy at y is equal to 0. Now, I said that if you would have known already from your frequent exposure to the subject that when one plate is moving, okay, if you want to plot the velocity here, the velocity will look something like this. So, this is the axis, okay, and this is the velocity magnitude Vx, and the Vx goes from here. This is the way the velocity goes. If you remember this piece of information already, then calculation of the shear stress becomes, because piece of cake, because this is a straight line velocity profile, that is the Vx versus y profile, and you should be able to calculate that minus mu 0.07, and this you can say delta Vx by delta y, because this is a straight line, and then you can say 1 V 10, okay, is the velocity here, and then the coordinate is 0 is the velocity here, the two boundary conditions, 10 is here, 0 is here, the distance is 0 is here, 10 is here, and then you would find out that this value of the shear stress comes out to be negative of the viscosity value. But to be able to do that so quickly, you got to remember that what is the velocity profile, and that this velocity profile comes out actually from the x direction equation of motion. So, equation of motion along x, or I can say x direction equation of motion. From this, if you write down the applicable x direction equation of motion, if you apply the boundary conditions, you get a linear profile here, okay? And this gives us, if you look at the equations, how does so the flow is dictated, as you all know, by the Navier Stokes equation, momentum conservation equations or expressions, and because this is a one dimensional flow. So, if you look at a generalized description, so you have one equation of continuity, 3 equations of motion, that is the 3 dimensional flow description. You have 4 equations and 4 unknowns. What are the 4 unknowns? 3 unknowns are the 3 velocity components, and pressure is also an unknown. So, the 4 unknowns, 4 in the equations. So, that means if you apply the right number of boundary conditions, it is in principle a well posed problem. So, if you take the x direction momentum balance equation, and the characteristics of the Navier Stokes equation is that in an exact way you have 4 terms on the left hand side and all 5 terms on the right side. You remember it like an unsteady term, 3 convection terms on 3 directions equal to the pressure gradient term, then corresponding 3 diffusion terms along the 3 diffusion means the viscous diffusion terms along the 3 coordinate directions, and then the component of the gravitational or the body forces. That is how it is written. Since the flow is not pressure driven, and that is a horizontal flow, the gravity component of gravity is 0. So, one should be able to simplify considering that 2 other velocity components are 0, And that fully developed flow essentially implies that there is no acceleration along the x direction. So, we can say that the equation will come out to be I will write down like this, so that you can appreciate it better. Okay? So, plus 0 and is equal to 0 plus 0 plus 0 plus 0. And here we have plus 0 plus 0. So, these are the three diffusion terms, these are the three convection terms, each of which is 0. This is the unsteady state term, which is 0. This is the pressure gradient term, which is 0 because the flow is driven by, and this is the component of the gravity, which is also equal to 0. So, which essentially means that the governing equation now becomes and if you solve this equation, you get V x as a function of A y plus c. That characteristics of the linear profile comes out from this, and to determine the two constants of integration, you apply now the boundary condition at y is equal to 0, V x is equal to 0, at y is equal to L or 10, V x is equal to 10. Then you find out immediately that B is equal to 0, because y is equal to 0, V x is equal to 0, so B is equal to 0, and that is what you get a straight line passing through the origin. Okay? So, this is the origin, and you get a straight line which passes through the origin, and here what you see is that A is equal to 10 and 10. So, A is equal to 1. So, V x is equal to y, that is the equation. And then you can see, oh, it is a straight line. So, I could very easily calculate the shear stress by considering minus mu delta V x and delta y, and then I can say mu is equal to V x 2 minus V x 1 divided by y 2 minus y 1, and you substitute the value, you come out to be minus 0.07, and the unit is going to be here dyne per centimeter square, because everything has been put in CGS unit. Okay? So, you should, one way is that in the context of fully developed, standard fully developed or frequently used fully developed flows, you should be knowing the velocity profiles. For example, if I now pose the problem differently, that both the plates are moving, but in the reverse direction, how will the velocity change? Okay? Fully developed flow, that we are going to discuss, but before that I wish to conclude here that if you remember the flow profile, it is very easy, you can save on time and find out that what are the values. Okay? On the other hand, if you do not know the velocity profile or you have doubt, you have to mentally work that out, that what is the governing equation, and then simplified form of the governing equation together with the boundary condition will yield the velocity profile, based on which by simply differentiating you can get the shear stress value at the desired location. Let us see now. So, this is u, okay, and this is u. The two velocity profiles are there, and the fluid is flowing like this. Let us see. So, what is the velocity profile under such case? If this is, they are moving in the reverse direction, one can, the same equation will apply, but now the boundary conditions are going to be changed. So, the governing equation here and the governing equation there are not different, they are exactly the same as a one dimensional. The same coordinate system is being applied, V x is in this direction, x is here, there is no V y, there is no V z, and that is how the problem is. And here if you now draw the velocity will look something like this. The velocity will look, profile will look something like this. So, this. Sorry, not here. I have drawn it wrong. That is the velocity. Okay? And you must have noted that the shear stress comes out to be negative here, because our y axis is this way and the shear is really transmitted in the opposite direction. That is what it implies. And here also, in both the cases, if we take the origin here, we will find out that the shear is directed towards the reverse of the, because the y direction is this way or this way. So, therefore, the shear is going to be directed towards the center, and it is also going to come out to be negative. So, as I said, that if you know this profile, then you will be able to extract the shear stress values at any point. You can find out that, well, the zero velocity actually is at the center line. This is a symmetrical problem. Okay? The distance here is identical to distance here. The boundary condition on this surface is exactly equal to boundary condition on this surface. So, as a result of which we can say that there is symmetry of the problem about the center line. So, you can draw this line, and based on which you should be able to find out that there are two streams. One is in this direction, negative x direction, the other is in the positive direction, and their volumes are absolutely identical, okay, because of the drawing of the plates in the reverse direction. So, you can do this by writing this equation, but now at y is equal to 0, for example, I will apply the boundary condition, maybe because of the coordinate system, that at y is equal to minus half L, which is 5 centimeter, and y is equal to plus half L, and then V x is equal to minus half L, it is minus 10 centimeter per second, and here it is V x is equal to positive 10 centimeter per second. That is the boundary condition, and then you get this kind of a velocity profile. The third type of fully developed flow is, which is very popular, okay? And again, as I say, that there are many small aspects which you should be able to calculate. For example, the fluid properties may be given, you should be able to calculate the Reynolds number of the flow. Okay? So, based on the average velocity, what is the Reynolds number of the flow, and then one can ask that whether the flow is laminar or turbulent, and you know that in the context of a pipe flow you have 2100 as the threshold value with normal roughness. So, if Reynolds number is less than 2100, flow can be laminar. So, lot of small questions can be formulated to test that how well you have understood really the fully developed flow. And in this context, you can see that the velocity profile is and we know that there are several things which you are supposed to remember by heart in the context of this important problem, fully developed flow through a duct, that we have the velocity profile as the parabolic, and the equation is Vz by Vz max is equal to 1 minus r square by r square, where capital R represents the radius of the pipe, we can say Rp, radius of the pipe, that is how. So, it essentially tells us when r is equal to 0, which is the central line. So, this is the coordinate system, this is the central line, this is the radial direction, and this is the axial direction, and here we see that when r is equal to 0, that means at central line Vz is equal to V max, and this is the value V max which we are talking about. Okay? And now, so if I you can say that if I ask you to calculate that, suppose the flow rate is given to you, let me pose the problem, okay, and then see the radius of the pipe in this context. Radius of the pipe is given as 10 centimeter. and then are 0.1 meter. We have a volumetric flow rate of water through the pipe, which is given as 1.66 into 10 to the power minus 4 meter cube per second. The viscosity of water is again given to be 0.07, then it is in SI unit or 0.07 gram per centimeter second. And we want to calculate the shear stress, for example, at R is equal to R. At this particular point, what is the wall shear stress? So, calculate tau, okay, Rz at R is equal to R. This is what is the value which is to be calculated. In this case, so you can now find out, for example, if Q water is given, the volumetric flow rate. So, you can find out that what is the average velocity through the duct cross section. It is a steady state problem. So, at any section the flow rate remains constant and volumetric flow rate. So, Vz average is equal to Q divided by pi diameter of the dp square. This is diameter of the pipe square, or we can say, if I just write it, let me not introduce another variable, pi r square. So, cross sectional area, volumetric flow rate by cross sectional area, and then we find out if you put the value, radius of the pipe is given, okay, the volumetric flow rate is given, and in this particular case Vz average will come out to be 3.1 centimeter per second, or 3.1 into 10 to the power minus 2 meters per second. And we should be knowing that this Vz max is actually, if you multiply, Vz max in pipe flow problem is twice of Vz average, or I can say that half of Vz max is equal to Vz average. That one can very easily prove. If you are not sure about it, just go back to your classroom or to your desk and then test this, that in the context of pipe flow the average velocity is actually the half of the maximum velocity. So, therefore, we can say that if you multiply this 6.2 into 10 to the power minus 2 meters per second, that is going to be the Vz max. So, therefore, we can say that we can differentiate this, okay, and we can say this is 6.2 into 10 to the power minus 2, let us put everything in meter, okay, and then this is going to be minus, okay, 1 by rp square, and this is going to be 2 times r, and there is going to be another minus because I have multiplied. So, this is going to be minus and minus. So, that is going to both vanish out, okay, and this is going to be is equal to tau, what I have written, okay, tau Rz. And we want to determine the value at wall shear stress at the wall R is. So, we say that now let us determine this value at R is equal to R sub pipe. So, this value is now R is equal to R sub pipe. So, therefore, this value is going to be R sub pipe and then therefore R p. And this becomes now a very simple exercise, okay, you should be able to find it out, and this comes out to be 8.68 into 10 to the power minus 2 dynes per centimeter squared. So, 6.2 into 10 to the power minus 2 multiplied by 2 divided by rp, okay, and that is the value that I have quoted, and where the radius of the pipe is given to be 0.1 meter. So, these fully developed flow problems you should be, this should be at your fingertips when you go and write exams on transport phenomena, etc. So that for doing the mundane part you do not lose really much time, because it is very important to be able to move very quickly through successive questions during examination and so on and so forth. For example, I mean, having studied the subject, your intuition, there has to be some intuition. I mean, let me just pose a problem, and then if you have understood this discussion, then if I pose a problem, say let us say that there is, I mean, how you visualize it, that is very important, rather than all the time trying to do number crunching. Quite a bit of thinking is necessary when you really deal problem, particularly when you are studying. So, suppose let us say we have a square cavity, it is a two-dimensional problem, complex problem, and we know that this two-dimensional problem is not amenable to suppose analytical solutions, as we have done in the context of say flow between a parallel plate with one plate moving. So, it is a square cavity, all dimensions are A. And suppose, so there is, this is y axis, this is x axis, okay. This is the Vx component and this is Vy component. So, two components of flow are, it is a two-dimensional, let us say steady state constant property flow. And now I said that look, just like the way I have posed the problem on the right hand side, let us say that this wall is a moving wall, flow within a square cavity, okay, with one wall moving. Then I want to calculate, so it is moving in the x direction with a finite velocity, say, which is s. And it is now said that I want you to draw, for example, how does Vx varies, okay, on this particular line, at the central line, how does Vx varies with the distance, if you want to plot. So, this you should be able to first understand that look, the velocity profile when the wall is moving, it is going to create something like this kind of a profile. So, the flow goes like this, it strikes the wall here and then it rotates, and that is what happens here, and there may be secondary vortices, but the overall flow pattern is a clockwise rotating vortex that you should be able to tell without solving the problem. There should be absolutely no ambiguity, even though you may not remember the equation, okay, two-dimensional equations you may not be able to write them, but the steady state solution that it will come out and create a toroidal clockwise vortex, that should be able to, you should be able to draw it. Now, you can, if it is asked that plot Vx, the variation of Vx along the central line, okay, vertical central line, this is a horizontal central line, this is a vertical central line, and we want to plot it, and then how does the variation will go. Here some kind of an intuition that looking at the flow pattern, how the flow Vx component is going to be varying, okay, that should be very clear to you. So, if you draw the central line here, suppose, and then we can say that the velocity really will go, we must understand this is a stationary wall, so velocity is going to be 0 here, velocity is going to be maximum here. So, we have maximum velocity here, and then the velocity is going to be something. I mean, you must understand that why this point is not drawn through the central line here, because of the simple fact that this is drawing with a velocity, okay, reasonably fast velocity. For example, okay, this velocity is much greater than the 0 velocity. This is not so small. If it is a small, then this figure perhaps is an exaggeration, but if it is a relatively large velocity, then this is the contour which is to be expected, and this essentially tells us that because I have drawn like this, because the continuity demands that whatever fluid is going in this direction, the same volume of fluid must come, and if the velocities, overall velocities are smaller here, that means the cross sectional area through which the reverse flow is taking place must be higher. So, the continuity equation you should be able to visualize, impose on the problem, and you should be able to accordingly determine that what is the nature of the velocity. So, this is how V x will vary as a function of y at, I would say, particle direction, and this is at x is equal to a by 2. That is the velocity profile. So, this kind of, in many cases, for example, if you have a rotating viscometer, there is a concentric cylinder, and if it is asked that if you assume a fully developed flow, how would the flow pattern change. So, the flow pattern will be maximum at the wall of the rotating cylinder, it is going to be 0 at the stationary wall, which is the furnace or the crucible, and then you should be able to say that there is a predominant direction of rotational motion in the system when you are dealing it as a fully developed flow, and there is a gradient of flow being maximum at the wall of the rotating cylinder, and gradually the flow velocity decreasing and attaining a value of 0, and so on and so forth. So, this knowledge comes to you with your frequent exposure to various kinds of fully developed flows, understanding the continuity and momentum conservation equations, and then you should be able to solve, in certain cases, extract the velocity field by solving the equation, and in certain cases like this you should be able to extract the velocity field considering applying your intuitions and basic knowledge of fluid dynamics to the system under consideration. So, we will take one more lecture and I will discuss this mechanical energy balance, and then we will wind up this 10 lecture module tomorrow.